Hello everyone, in this video we're going to talk about how you calculate momentum, what we actually mean by momentum, and the law of conservation of momentum. Now let's start actually with this picture to the right. In many offices, people tend to have this particular, let's say toy, but it's not really a toy per se. It's called Newton's cradle. And what you do is you essentially grab, let's say this ball bearing here, you pull it back, and when you let go, it swings forward and essentially hits all these ones. And then what you'll notice is that this ball here swings outward and then this swings back, and you get this continual motion that these balls just continually appear to keep hitting one another. Now that is essentially momentum, or the conservation of momentum. Moving objects have what we call momentum, and in a closed environment, by closed environment I mean one where no other external forces are acting, what you have is essentially this conservation of this momentum. So let's think about what momentum actually is in terms of a formula, because that really will help us work out what's going on here. So to work out the momentum that an object has, we need to know its mass, and we also need to know the velocity that it is moving with. Now velocity is like speed, but it gives that a direction. So momentum has a direction. So the momentum of an object is a product of the mass times velocity. Let's think about the symbols we use as well. Momentum is often given the letter P, mass is m, and velocity is v. And if we think of the units, well, mass is typically kilograms, velocity is meters per second, which therefore gives a momentum unit of kilograms meters per second. So that is how you calculate momentum of a moving object. Let's think about a real life application, why this is important to consider. So let's imagine the scenario. We've got here just a very quick sketch. We've got a road, and driving down that road, a very quick sketch here. We've got a vehicle driving down this. Not the best picture of a car, but we'll go with it. There we go, the lamppost, let's say it's on. Nice little yellow light coming from the lamppost. There we go, very simple. When that car collides with the lamppost, if it were to collide, what you find is that it decelerates very, very quickly. So the opposite, complete opposite of acceleration, it decelerates, it slows down rapidly. Now when that happens, the momentum value approaches zero very, very quickly, and when that does, the car and its contents, so we're talking about the people inside, experience a very, very large change in force. Now that is dangerous, it can cause injury, cause death. So what we essentially need to do is take the momentum and try to get it to zero, but as slow as possible, because when we slow down that change, we essentially reduce the forces that the car and the contents of the car experience, so it becomes less dangerous. So what you'll notice in cars in this region here at the front, what we actually have is something called the crumple zone. So we'll just label that on there, the crumple zone. Now the crumple zone, as the name suggests, is an area of the car, it's the front of the car, designed to crumple, to take most of the impact. And what it does is reduce the momentum level very, very slowly. In a way, it slows down the deceleration, so the forces you experience are less. It's pretty much the same way that the airbags work. So the airbag will slow the momentum of your head if you're driving, so that the head experiences less force overall. And also the same principle by seatbelt. Now, exam questions love this kind of scenario-based context, and they say, can you think of a real-life application of where a knowledge of momentum is useful? And you could talk about Newton's cradle, but the best one to do is talk about the car, because the car's crumple zone, the airbag, the seatbelts, all designed to reduce the time taken for momentum to reach zero, to minimise the force and the impact that one experiences. So we've said about momentum being a product of mass and velocity. Let's think of an actual exam question where we can really highlight this conservation idea. because you can't create or destroy any extra momentum within a closed system. As I said, one where no external forces are acting, we have to conserve it. Now, a good example of this is a collision between two cars. So we'll stick with the car idea and we'll take a collision. We'll call this car 1 over here. I'm not going to... Okay, I'll do a little mini sketch. We've got car 1 here. And let's call this one over there car 2. So we've got car 1, car 2. We're going to imagine car 2 is stationary. Car 1 is driving, and car 1 is going to collide with car 2. Now you may be given this information. You might be told that the mass of car 1 is 500 kilograms. You might be told its velocity. Let's say the velocity, for sake of argument, is 30 meters per second. So momentum, P, if you do m times v, comes out as 15,000 kilograms meters per second. Okay, so you may be given that information. You may then be told car 2, that is stationary, has a mass, and let's just say for the sake of argument, that mass is also 500 kilograms. Its velocity is 0 because we're saying that it's stationary, and so its momentum overall would be 0. So 0 kilograms meters per second. Now this is how a common question kind of goes. So this is our scenario, two cars colliding, and it may say after the crash, car 1 has a new velocity. So a new velocity after the crash, of 5 meters per second. And the question is, can you work out the velocity of the second car? So the first car goes into the back of the second that's not moving. You're told that the velocity of the first car now is reduced to 5 meters per second, and that impact causes car 2 to move, and you want to know what velocity it has. I'm going to talk you through how you can work out this particular problem. So let's just shrink the screen a little bit there to give us a bit more room to do this calculation. I think it's quite an important one to work through. So we've said that momentum is conserved. So the total momentum at the start must equal the total momentum at the end. So if we think about at the start, if we say m is mass and v is velocity, because mass times velocity gives momentum, m1 v1 plus m2 v2, so for car 1 and car 2 at the beginning, that must equal m1 v1 after the collision and m2 v2. So m times v is momentum. So what we're essentially saying here is the momentum of car 1 and car 2 before the collision must equal the momentum of car 1 and car 2 after the collision. So let's put in these values. If we know that if we take car 1, we've told that our momentum at the beginning is 15,000. Now just for the sake of argument, I'm just going to miss off the units here. You should always include units, but just for the numbers sake, I'm just going to put the numbers in. So what we've got is 15,000 plus momentum of car 2 at the beginning, which is 0, equals the momentum of car 1 after the collision, which is 2,500. So mass of the car is 500 times 5, that's 2,500, plus, now we need momentum of car 2. Now we know the mass is 500, so that's 500, and let's just call the velocity x, 500x. Do a bit of algebra here. Now if we rearrange that equation and move the numbers, so take the 2,500 across to the other side, to minus, that would be 15,000 minus 2,500. So that would actually leave 12,500. So 12,500 would equal 500x. Now if you're a bit unsure about how to substitute equations, I have done a video on that. But what you do is take the 500 onto the other side to divide. So that becomes 12,500 divided by 500. And if you do that, that works out at 25. And then we'll put the units in meters per second. And there we have our V2, our velocity. So all we've done is substitute the values for M1 V1 and M2 V2 before and after. And that's left us with 12,500 equals 500x, 500 times the velocity. So if you rearrange that, x must be 25 meters per second. And we can see what we've done is conserve momentum. Now, one way they might put a spin on the question is to say, imagine car 1 collides with car 2 and both move off together. For some reason they stick together. So almost like a rugby tackle, that's another example. So person 1 goes to rugby tackle person 2 and then they move off together. Now all you would have to do there is just combine the masses and treat them at the end as one big moving object with one set velocity and one combined mass. Now if that happened in this scenario, all you do is take the mass of both cars, add them together, so that's 1,000 kilograms, and just use a value like that. But in this question we've kept the two particular cars separate. So there you go. You calculate momentum by timesing its mass, the object mass rather, by its velocity. The units of momentum would be kilogram meters per second, given the mass units would be kilogram and velocity units of meters per second. We've said why it's important to consider crumple zones, airbags, seatbelts, and why momentum affects the amount of force experienced in that scenario. And we've talked through one particular exam question that you could get on the conservation of momentum. Okay, hope all that helps.